Well, the guy who invited me is not here. Okay. Well, I would like to thank the organizer who invites me to give a talk on this B physics. And actually, I'm the first one who present the experimental results. Okay. Although I know this, most of the audience are theorists, so I will try to give a very, very brief introduction. Okay, the talk of today I'm going to share with you the result presented by this year on this Electroweak and the Radiative penguins transition from B factory. Okay, at first I will I would like to talk about the motivation. The Electroweak and the radiative BPKs are sensitive to new physics in the penguin loop. For instance, in this radiative penguins, maybe there's some contribution from the charge Higgs or some actions charge in the loop, which may enhance or reduce the branching pressures. And since these radiative BDKs is charmless, the branching fraction, standard model predicted branching fraction is relatively small. Therefore, if there's some new physics with a relative strong strength there, so we may be able to see it in this case. And theoretically, this cross-section predictions or the branching fraction predictions are more precise or more precisely calculated compared to hadronic decays. That's also an advantage to study these channels. And in this, especially the Electroweak penguin case, there are many observables we can use to probe new physics, such as the CP asymmetries, forward-backward asymmetries, isospin asymmetry, and also some other observables such as P5 prime. And this distribution has been reported by the LCB collaboration, and they roughly see I saw this roughly a 3 sigma deviation from the standard model exploitation. So in this talk, I will present the results with all inclusive measurements, such as the B2SS gamma, B2SSL. And I'll tell you the reason why later. Okay, here is the current status of the B2SS gamma measurement. In the this branching fraction calculation, the theorists are able to perform this next to next leading log calculation with the minima photon energy 1.6 GeV in the E plus E minus, or in the B rest frame. And this is the errors they calculate. This is actually a lot of heroic work by a group of theorists to perform this calculation to such a very small, very accurate level. And this is the current experimental results from Bell, Baba, and Cleo with different channels, and compare with the well, this is the average. So experimental measurements, we require this there's a relatively high energy photon in the event. So it's a minima E gamma cut. And two approaches are used. One is inclusive approach, which means we don't fully reconstruct this XS. So we rely on this some data in the off resonance region, and we treat it as one of the dominant background and subtract the off resonance data to to estimate the cross section. Or we can require actual left-hand tech or full reconstruct the other beats to enhance the signal to background ratio. The second approach is a semi-inclusive approach that we requires many SS final states, such as K-pi, K-pi-pi, those states. You try to reconstruct as many as possible, then estimate the missing one based on the factorization or fragmentation model. All right. Okay, this is the today I'm going to show the result from Bell and Baba. This is the two accelerator in the KEK and Slack. And this is the Bell detector, and this is a Baba detector. They are very similar. And this is in the first century of this, in the first 10 years of this century, these experiments performed very well. However, both experiments stopped taking data, starting from 2008 for Baba and 2010 for Bell. And the luminosity achieved is above 1.0 inverse autobahn. And this is the Bell's luminosity curve as a function of years. And here, this is the Baba's. And the performance of both detectors are remarkable. Okay, now I'm going to talk about the first result. This is the branching fraction of B to SS gamma from semi-inclusive approach. So we use the full data Bell data sample 711 inverse van der Waals, and first we choose the photon which are not from the pi 0 or eta decays, and then reconstruct the XS states with 1 kaon up to 4 pion, or 1 kaon plus an eta up to 2 pion. So totally there are 38 final modes in the final state. I will show you this roughly reconstruct 38 modes. But that's corresponding to roughly 70% of the XX this fraction. It's only 70%. And the single model, we adopt this Kagan-Neuber model plus the jet-set fragmentation for MX about 1.15 Jeff. Now below that, this is just a K-star resonance. Here, dashed line shows the theoretical model, and the solid lines with some detector resolution, a detector effect. Then we generate the signal with the BMAS and this factorization is some scale. Okay. So then we try to veto the sum of the dominant background, D star row events were D to K pi pi gamma, K pi pi. So then we perform these background suppression by including many variables like shared variables and this data E and some tagging information, and put all those variables into a neural network. Here shows the neural network output. On the right hand, you can see this is the signal distribution is look like this, and the background is populate more in the -1 region. Okay, with this we can make a simple cut to perform the first level of background suppression. After that, we choose the best candidate with the best neural network output value. Then feed on the mass in 19 MXS beams. For instance, this is the first beam, point A to point 9 region, that's the very nice peak show up. And this region, we know the dominant axis is the K star. While for the high mass region, the background is high, but the clear signal was apparent. After perform this, we with the MS above 0.6 and below 2.8 GeV, and the E gamma star is about 1.8 GeV. The branching pressure is measured to be 3.151 plus minus 0.17 plus minus 0.33. Here, this shows the MX spectrum. You can see a clear K star. The high mass region is due to this various resonance and also fragmentation. And very importantly, the dominant dominant systematic errors come from the hadronization model, which means how do you know the MX, these various MX modes? So we use we divide this MS into 10 categories. It's 1 to 10 categories is K pi, without pi 0, K pi with pi 0. And compare this, our data with the Monte Carlo expectation and make a correction. And finally, systematic error of 6.66% is given. Okay, then we use our measured cross-section and extrapolate to this E gamma star greater than 1.6 GeV case. We make a correction because our lowest E gamma energy is 1.8. So we need to make a correction, correct back to the E gamma at above 1.6 GeV. And this is our results, 3.74 times 10 to the minus 4. So far, this you can compare our results, new results, with other measurements. This is the best in this semi-inclusive approach. With this branching fraction, we can also exclude the charge Higgs as a function of tangent beta at 68% confidence level, 95% and 99% confidence. I mean, the area below this curves are excluded. Okay. Then let me talk about the direct CP. In the standard model, the CP asymmetry for SS gamma or SD gamma is rather small. For SS gamma is around 0.86% to 2.8% theory error, and the branching the ACP for the inclusive S plus D gamma is very close to 0. I don't have time to go to the detail, and the reason is the partial width difference between the B and the B bar for S gamma case is just opposite of D gamma. So that's why if you include both channels, the CP asymmetry is very, very close to 0. Therefore, if you see some deviation from 0, it means there must be some new physics in the penguin loop. Before our measurement, this is the previous result from the Bell and the Baba, 152 million BB bar and 383 million BB bar for this semi-inclusive approach, which means B to S gamma measurement. On the right-hand side, there's Baba and Clio measurement for the B to S plus D gamma measurement. So today I'm going to show the Bell results on this inclusive approach and Baba update on the B to SS gamma approach. Okay, this is the recent result published by this Baba. The semi-inclusive approach is very, very similar to what I just talked about about the Bell technique. So they reconstruct SS in 16 different states, and also require a minima energy photon, and choose the best candidate on many different variables, such as shared variables and the momentum pi, probability of a pi zero, and so on and so forth, and choose the one of the best candidate among all the candidates in the event, and reject continued the backgrounds using shared variables and the pi zero score, which means this is an indicator if this photon is from the pi zero decay, and correct for possible symmetry bias. For instance, maybe you have a K plus and K minus have a different acceptance or efficiency in the detector. So they use the data D star plus to calibrate, to know the K-on finding efficiency. If there's any difference between charge, positively charged and negatively charged mode, and they also consider possible peaking background from the Monte Carlo. Okay, and this is the all the 38 mode they consider just as Bell's analysis, but only 16 of them favor this they are flavor distinguishable. So for the CP asymmetry measurement, only 16 modes are used. Okay. Now with the BABA data, this is the observed CP asymmetry for B to S gamma is 1.7%. Then I move one more step forward. They check the CP asymmetry for B plus mode and the B0 mode to see if there's any deviation. And the difference is around 5% with larger errors. Therefore, they are consistent with 0. However, theoretically, this CP asymmetry difference between charge mode and neutral mode is related to this Wilson coefficient CA and C7, and the expression can be shown by this equation. The delta A is related to lambda bar 7A divided by the mass of B quark and times the imaginary part of CA over C7. And in standard model, both these CA and C7 are real. So if you find this variable is real, that means there's something new in some hint of a new physics in beyond standard model. Then this equation can be expressed as this. So theoretically, this lambda bar 7a, this parameter is known to be within a range of 17 to 190 MeV. But since Baba measure have the experimental measurement on the data A, and we have this expression, so they are able to perform some consistency check and define the chi-square of the theoretical expectation minus the experimental measurement divided by experimental error square. Since the lambda 7a is within a range, so they just choose the lambda 7a such that this the theory and the difference of the theoretical expectation and experimental measurement is the lowest. Okay, with this definition, they are able to give some confidence level range estimation. Okay, and here that's the published results. This is a minima chi-square as a function of imaginary part of CA over C7. This blue line shows the 68% confidence level, which means in this percentage, the values is allowed. and the origin one will cover this 90% confidence level. Okay. And here on the other side, this is lambda bar 7a as a function of imagined part of this. As I say, this if for standard model, this imagined part of CA or C7 should be zero. They should be real. So any deviation from 0 means there's probably some new physics there. Okay, let me talk about another technique that's called inclusive technique. I'll just report this XS plus D gamma measurement this year. In the inclusive measurement, we only identify the photon from the BBK, but we don't know the flavor. So the flavor has to be determined by assuming that the accompanying B is from the decay semi-leptonically. So we can use the charge of the lepton to know the flavor of this B. That's the concept. And that's just with the still very similar to the previous one. It's 1.7 minima energy, photon energy requirement, 1.7 to 2.8, and also provide some pi 0 eta 8 veto and some other technique. And we suppress the the various background with many different variables, such as the thrust or modified fast-Wolfram moment, which means this variable can distinguish the jet-like structure and the BB bar. This is more spherical distributed events, and also some other kinematic variable to distinguish if this accompanying B meson decays semi-leptonically. And to put all the variable in this software package called boosted decision tree. And this is the package that can distinguish two distribution with the various variables in it. So this is the output of this. You can see the red one is the signal, and you have a continuous background, just the E to QQ bar background events, and the blue one is the BB bar background events. So you make a cut. On the right hand side, you plot the E gamma changes. That's purely Monte Carlo. That's red one is the signal distribution. Expect signal distribution times 50 times the expectation. The red and the pink one shows the Monte Carlo expectation for the background with current data. So we need to distinguish this. There's a lot of efforts have been put try to estimate this BB bar background and the continuum. And for the continuum, you just E to QQ bar, we use off resonance run. And the BB bar background mainly come from the pi 0 and eta decay. So we estimate from measuring the cross section of B to x pi 0 or x eta, and compare the cross section about this branching fraction with the Monte Carlo expectation. If there's any deviation found, and make a correction. That's how we do it. So our study shown here with this observed spectrum, we found this 21.2% are signal events, and the downwind background comes from the BB bar, where pi 0 is from the B one of the B decay. Okay, it's around 50%, and eta decay, and the continuum is from this off resonance data to for its explanation. Okay. Okay. So this is the then you have to correct for some round tag fraction, because the sometimes this is a B0 and D0 bar in the event. We have a mixing effect, and that mixing effect you need to be considered. And that one is simple. You know the missing parameter XD. You can make a correction. And the other one is the lepton is not from the B. It's from the the B daughter B to C transition, and the C quark becomes a D meson, and D meson decays leptonically, and this fraction is estimated using Monte Carlo. And sometimes we have a mis-ID, D star. Actually, the other side is a D star, and the pion is misidentified as a lepton. And correct for all this, then I'll show you the final results. And we are able to measure the ACP as a function of the the photon energy threshold. This is the CP asymmetry. For 1.7 GeV, the ACP measured ACP is 1.32%. For 2.1 GeV photon, this is 2.23%. Okay, this compares with the other results. We have the old Bauer measurement. This is our Bell measurements. At 2.1, this early Clio measurement. So far, this is the best measured B2S CP asymmetry of B2SS plus D gamma. Is 2.23% with larger errors, which means it is still consistent with 0. No new physics hint is observed. And let me switch the gear to talk about the B2S L plus L minus. I am running out of time. And this one, we know this decay can be described by these various Feynman diagram. They are sensitive to these C7, C9, and C10 coefficients. We can probe new physics in many observables. One of them is called forward-backward symmetry. So what I show, and I'll talk about our Bell new results on this forward-backward symmetry measurement. And the forward-backward symmetry is defined as the angle between the L plus direction and the B quark moving direction, or L minus direction of B bar quark moving direction. That's how we define the angle. Okay, then similar to the first result I just presented, we just use a semi-inclusive approach, trying to reconstruct the XS. In this case, there are 18 states of XS are fully constructed. And since we don't want to have this J psi to LL contamination in our sample, so we veto these dilepton pairs whose mass are in the J psi and cyclone region. Okay, so there are many, rather many possible background, like a leakage, also mis-ID, and some swarm mis-ID means some of the pion is misidentified as electron or muons. So made all the correction. This is all these 18 states we want to use for our measurement. And we need to correct for the measured forward-backward symmetry to the true asymmetry, because we have a acceptance. Okay, that's the final results. We divide these the Q square, which means the dilepton mass square, into 4 different beams. And this red black band shows the standard model expectation for backward symmetry, and the points with arrows are data. So far, although the first points is higher, they are still considered consistent with the standard model expectation, since the error is large. And Baba also report their semi-inclusive measurements. Again, it's the same. They reconstruct XS with many different final states. and beetle on the Jeb psi and psi prime to LL, and some kinematical requirements. Okay. All right. I'm out of time. Oh, I'm show you the final result. They perform the fit on the B mass and also Likelihood ratio. It means signal to background. Well, this likelihood ratio means actually a signal over signal plus background. This to indicate if it is a signal like or background like. They perform the two-dimensional fit on 6 different Q-square beam on the cross section, and also these CP asymmetry. They also report this the CP asymmetry as a function of this Q-square. That's the result. That's the absolute cross section. The branching fraction they measure for the S mu mu mole, E mole, and combine mu mu and E results, and compare with its standard model expectation. So far, they are still consistent with each other. And for the the fifth the largest Q-square region, they report the branching fraction, and the standard model expectation. They say it is within 1 sigma deviation, since the experimental measurement have larger errors. Then they also report the CP asymmetry in 4 different Q-square beams. So far, no surprise is observed. Okay, I'll give you my summary. So in 2014, there are several SS gamma and SLL measurements were reported this year. Most precise measure from Bell in this semi-inclusive approach is presented this year, actually this summer. And the Baba has reported the CP asymmetry on B to SS gamma. So far, this is the most precise measurement. Moreover, they also provide the difference of CP asymmetry on this B to SS gamma, and made a constraint on this imagined part of CA or over C7. And Bell just report the first measurement on the CP asymmetry for B to S plus D gamma. No strong indication of new physics yet, and also Bell also report first inclusive measurement on the B to SLL results. And finally, this last Baba report B to SSLL, and the branching fraction measurement on semi-inclusive B to SSL, and the CP asymmetry results on this B to SSL. So we expect that this precision measurement can be performed in Bell 2, and we will intend to fully in the future we can fully reconstruct the accompanying beams to take advantage of much more BMS on data sample for this inclusive analysis. Okay, thank you.
Thank you. Any questions or comments? Yes.
Question was B to XSLM mode.
Which one?
Any attempt to measure the electron mode and muon mode difference?
Yes. Yes. You mean the branching fraction?
Yes.
Yes. You see this. You can see the difference already. You see the Baba measurement. This is muon mode, electron mode, and that's the average. Look at the arrows.
Just compare with LSGB.
Right. About, well, LSB probably they cannot do the inclusive measure.
Yeah. Yeah, that's good.
Any other questions, comments? Could you comment on B2D or B2D start how new from there?
Oh.
Although you didn't talk about here, but
Yeah, it is. We push it very hard. I saw this. We almost want to show last year, well, this year.
yeah.
So there's a chance that we can show this in the coming winter conference, but I'm not sure yet.
Okay.
Yeah, we have a general meeting on February. Hope that we can make a push.
Push, please.
Yeah, sure.
Okay.